continue with today's session. Before we go further, let me remind you to like and subscribe my channel and press the bell icon to get the latest updates. So in our previous video, we have seen when is work said to be done. When a force causes a displacement in the direction of force, work is said to be done. We had also seen that kinetic energy is nothing but a product of mass times velocity square and time it with half, which is half mv square. Now we are going to prove that these two are interrelated. That is, whenever there is a change in kinetic energy associated with an object, work is said to be done. For this, we are going to consider the SWOT equation. V square is equal to U square plus 2AS. With slight modifications of multiplying half m on both the sides of the equation, we land up with the answer that change in kinetic energy, that is, this is final kinetic energy minus the initial kinetic energy, is equal to force times displacement, which is work done. So this concept, that is, whenever there is change in kinetic energy associated with an object, work is said to be done. And this concept is called as work energy theorem. Let's see a few applications of these. The direct application is an MCQ question. You can see here. A force of 8 Newton accelerates a body of 4 kg from rest to a new speed of 5 meters per second. What is the work done? So we know that work done is also change in kinetic energy. Try to solve and come back for the answer. So if you can see here, change in kinetic energy is the final kinetic energy, which is half times 4 times v square, which is 25. And initial kinetic energy is 0 because velocity is u is 0. So initial kinetic energy is 0. So change in kinetic energy is nothing but 25 times 2. Answer should be A. Next, we are going to talk about the energy changes associated with a very usual example, which is a simple pendulum. So identify what is the energy at each point of the system. So when it is oscillating, at both the extreme positions, it has potential energy, and at the mean position, it has kinetic energy. And you can very well see the loss of potential energy is equal to gain of kinetic energy. So at any point, total energy is a constant, and change in kinetic energy is equal to change in potential energy. Let's see an application for this. An object is released from rest. So you know what is the meaning of from rest. When it is released from rest, initial velocity is 0. It is released from rest from height of h meter above the Earth's surface. As the object falls down through a height of 0.775 h above the Earth's surface, what is the kinetic energy of the object at 0.75 height? And what is the gravitational potential energy at the height h? You have to find the ratio of this answer. So you can see diagrammatic form that this is height h. It's falling from this height. And they want to know what is the kinetic energy, which is somewhere here, which is 0.75 h. So how can you relate to what you already know? Kinetic energy of the object at 0.75 meter. If total is 100%, 75% is kinetic energy, then what is the remaining for potential? Because total is the conservation of energy, total is always the same at every point. So if 75% of the energy is kinetic, then 25% is, or 0.25 is the contribution of potential energy. So can I write that 0.75 H is nothing but 1 by 4 of mgh divided by potential energy at height h is mgh. So can I cancel the common terms? The answer is 1 by 4, which is B. Now we are seeing the direct application of work energy theorem. Look at the system here. There is a spring having a mass m, which is hanging vertically. The spring constant is k. The spring is displaced through a distance of amplitude a. So x is one extreme position, y is the other extreme position, and e is the mean position. Amplitude from mean to extreme is a. The question is, what is the work done by the tension in the spring as the mass moves the distance from x to y? So let's start with the application of work energy theorem that very clearly tells that change in kinetic energy is equal to the net work done. And we can very clearly see that kinetic energy is same at both the positions, at the mean position. So change in kinetic energy is equal to 0. So if I tell that change in kinetic energy is 0, then can I also tell that net work done is also 0? Now let's see what is the net work done. Net work done is the work done by the force that is pointing downwards, which is the weight of the object. And there is another force along the spring, which is the tension. So can I split net work done as the work done by the weight plus work done by the tension? Since the net is 0, I can put both of them to be equal to 0. So what can I tell? That work done by the weight of an object is equal to minus of work done by tension. Work done is force times displacement. So let's continue. Force acting is nothing but mg. Displacement from x to y is a plus another a, which is 2a. So the answer is work done by the tension is minus 2a mg. Let's see another example. Look at the system. There is a mass that is hanging. And there is a force that is applied on both the strings passing through a pulley. So step 1, we have to find what is the work done by this force. So the first important thing that you should know is to make an FPD. FPD looks like this. Mg, or weight acting downwards. The force along the string, let's name it as F as in the question. And you can see this since it is at an angle theta with respect to vertical axis. Each of the two forces will have a cos theta component along this line. There will be two of those, one for the left side and one for the right side. So the resultant will be 2f cos theta. So can I tell that 2f cos theta is balancing mg if the system is not moving? So step 1 is to write 2f cos theta is equal to mg. Let's make f as the subject. If f is the subject, we have mg over 2 cos theta. If I now go for the work energy equation, work done, conservation of energy, So work done is getting transferred as force times displacement. So you know that F is the force and displacement, if you have seen, is through a height h. So I replace that displacement as h. Now apply what we have just derived. Replace F as mg. So work done is defined as force times displacement times cos theta. So what I'm doing is I'm going to replace the quantity of F that I derived, which is mg over 2 cos theta times h into cos theta. Cos theta and cos theta gets cancelled. So you should have got the answer mgh over 2. This is the equation for work done. There we derived was power is force into velocity. Now then what is an average power? Average power is when you have a constant force, the first scenario, with the change in velocity, you take an average. The next concept is when the acceleration is not a constant. If acceleration is not a constant, then average power is also equal to average force times u plus v by 2. So you have to see whether the situation is having any constant force or non-constant and apply the equations accordingly. Look at the question here. A constant net force. So very clearly we have a constant force which accelerates the body from 2 to 12. Find the average power. So we know that for a constant force, average power is force times u plus v over 2. Replace it with the values that we know. 6 Newton times 2 plus 12 is 14 over 2, which is 7. 6 sevens are 42 watts. Should be the work done. Should see. Let's solve some exam style questions now. You can see this concept that a ball of mass 0.8 kg is attached to a string. The distance to the center of mass of the object till the support is 95 centimeter. So you can see 95 centimeter. Ball is released from rest when the string is horizontal, that is, it's released from this position A. When the string becomes vertical, it collides. Position B, it collides with the mass, which is of 2.4 kg. That is at rest. So initial velocity of that is 0. What is the question? First is draw a free body diagram of all the forces acting on the object. So very clearly, forces acting is the weight of the object and the tension. Since it's taking along a circular path, the inward force is more than the outward force. So tension is more just before it collides with the block. So you have to draw tension arrow, which is longer than weight. Next, show that the speed of the ball is about 4.3 meters per second. So here we are going to apply law of conservation of energy. So you can see that when a block is released, so we can very well see that when a block is at a height, the energy that it has at point A is mgh. When it is released, it gets converted to kinetic energy, which is half mv squared. So here they are just applying mgh is equal to half mv square. G is 9.8. H is 95 centimeter, which is 0.95 meters. I can cancel m on both the sides. If I take 2 on this side and take the square root of the answer, I can find V. So after calculating, my V should be 4.32, which is rounded off to 4.3. So this gives me an answer of 4.3 meters per second. Find the tension in the string. So to find the tension in the string, I should apply the FPD equation. So you can see for circular motion, the inward force is tension, outward force is weight. So tension has a positive magnitude, weight has a negative magnitude. So if I apply that, tension minus the weight is equal to mass times acceleration, which is mv square over r. V, we already got it here. So let's substitute. Tension is what is asked. Tension is equal to mv square over r plus w. So you see the mass of the block is 0.8 kg. So 0.8 into 4.3 square over 0.95 plus 0.8 into 9.8. This should give the answer 23.5. You can check it. This gives an answer of 23.5 Newton because it is tension, which is a force. Let's take it further. After the collision, the ball rebounds back with the speed of 2.16 meters per second. Show that the collision is elastic. So to show that something is having an elastic collision, you can apply either law of conservation of momentum or conservation of kinetic energy. So if I know the velocity of an object before and after, so we can very clearly see to simply prove that total kinetic energy before the collision is equal to the total kinetic energy after for each of them, for the ball as well as for the block. So we substitute values. This is the kinetic energy for the ball before. Kinetic energy of the block after is half mv square, which is substituted. And we also substitute the ball. The kinetic energy of the ball is half m times 2.16 square. So if you to each side, you can very well show that both of them has the same answer, which is 7.16. This shows that it is an elastic collision. (7.46). We can show that this is 7.46 on both the sides, and hence it is an elastic collision. Now the last thing that is asked is calculate the maximum height risen by the center of the ball. So after the collision, what we can see is the ball is going to rebound and it will have the energy which is half mv square. And the rest of the energy is taken in by the ball. Find the height risen by the center of the ball. Okay, so After it has hit the block, the rebound, during the rebound, kinetic energy is getting converted to potential energy for the ball. Kinetic energy after the collision, the rebound energy was M can be cancelled. Rebound energy was 2.16 square. So this is the kinetic energy associated with the ball. M and M is cancelled, so you can just put 9.8 times H. Here it comes to around 23 centimeter. The rebound height, which is the answer. Next, the coefficient of dynamic friction between the block and the rough surface is 0.4. Estimate the distance traveled by the block on the rough surface until it stops. So we can see that coefficient of friction is mu given to you. Mu d is given to you. Final velocity is 0. So we can apply the final velocity is 0. We have to calculate the distance s. So step first is find the frictional force. Frictional force is mu times mg. So which is 0.4 times 2.4 into 9.8. That is step 1. So you get the answer of force of friction as 9.42. Next is what is the distance traveled? Energy theorem, and prove that work done by the force of friction is change in kinetic energy. Work done by the friction is the force of friction times the displacement is equal to half mv square for the block. Force is 9.42. Displacement is what we have to find, is equal to half. Mass of the block is 2.4 and velocity is 2.16 square. It is 0.594, which is the exact thing that we get. You can see here the solution. This is the actual marking scheme. We have done exactly, and we can prove that the distance covered before it has stopped is 0.594 meters. So with this, we come to an end of the concept of work power energy. Do like and subscribe my channel and press the bell icon to get the latest updates. Bye-bye.